Well, let me start by thanking the organizer, Randy, Steven, Daniel, and Marcus for the invitation to this presentation in this very nice workshop. It's really nice to be back at ITAMP. So yes, the title of my talk is going to be on qualitative spin dynamics and weakly tracking fermions. And when even though this talk is about optical lattices, in this case there is not going to be a real optical lattice, but it's going to be a synthetic optical lattice in the energy space. And what I'm going to tell you is going to focus is in the observation of a dynamical phase transition. And perhaps the punchy line that I want to convey is that weakly interacting fermions in a trap could be used to simulate the dynamics of BCS superconductors. Maybe that's what they're going to be learning about. So this work has been done in very close collaboration with Joseph Quisen's group in Toronto, and highlight the group of graduate students and postdocs, Scott and Ben, who took most of the measurements that I'm going to report. It's not working?
No. I think the battery sets.
Hello? Oh, it's off?
No, it was
It's on?
So we don't have to use one battery per talk.
Okay, I will have to speak loud. Yes, it's not working.
Get more batteries.
Okay, I will continue. Yes, so, and of course, the group in my theory group, especially I want to highlight Pero, she did most of the calculations, and Jamil Marino is actually here in the audience. And even though, well, this work was done in Joseph experiments, I want to also thank you because most of the theory that is developed for modeling the dynamics was actually the foundation of the theory started by modeling the strong symmetrical lattice clock, and you heard a little bit about yesterday in Jim's talk. All right, so even though thermodynamics and statistical mechanics are the pillars of modern physics and has allowed us to classify, for example, equilibrium phases, I can say that non-equilibrium systems are actually ubiquitous in life. We find them everywhere in nature, starting from land itself to motion, to weather, to market. So everything is non-equilibrium in nature. And perhaps the most intriguing case is when we are talking about quantum systems, because quantum systems are extremely complex when they're out of equilibrium and strongly interacting. And we had a very nice talk yesterday by Enku, who told us that yes, in fact, these out of equilibrium systems actually tend to be strongly correlated and entangled. And because of that, and because of lack of methodologies, because a simple description of in terms of the statistical mechanics typically is not appropriate. Let me see how else. Okay, perfect. Hello? Is that better? Okay, perfect. Now it works. Yeah, so we cannot describe them very simple. So what we need is to have a new way that we can classify the organizing principles of non-equilibrium matter, because actually these systems are very intriguing and can admit and allow new phases that are probability to exist at equilibrium. But fortunately, the time is just right because experiments are now starting to access, even in real time, the dynamics of our equilibrium systems and are allowing us to understand them in a very controllable way. And examples of this great progress in the last couple of years are a various set of experiments that have revealed different types of behavior, like, for example, synchronization and locking in the cavity experiment at JILA and James Thomson. It has been reported self-organized criticality, for example, in the Heidelberg and Stansburg groups. Here at Harvard and also at JQI, we have seen new states of matter, the time crystals. There has been experiments in trapions that have seen scrambling and quantum chaos. And also, well, there has been recent experiments in trapions and in bosons in Hamburg that have seen dynamical phase transitions. That is going to be the topic of this talk. Now, for this specific type of talk, we are going to adopt also the definition that has been used in a recent trap-ion experiment of a dynamical phase transitions. This experiment was trying to emulate the asynchronous transverse field model in JILA, in a radial trap-ion. And what we are going to adopt as a definition is that the existence of an order parameter that behaves very different as we tune the parameters of the system and have a very different behavior that can distinguish two different types of steady states. So the important point is that this order parameter exhibits a non-analytic behavior, and near the transition, we are going to see that the observable typically exhibits a scaling behavior that is the one that is reminiscent of conventional phase transitions. But the important difference is that the behavior that we find cannot be attributed to a minimization of the energy. And there are no emergent symmetries in the systems. For example, as we will see in this talk, we are going to have a symmetry between positive and negative interactions. Alright, so a little bit of the experiment. The experiment is at Toronto, consists of trap 3D gas of the quantum degenerated potassium atoms. Potassium 40 atoms, over here vary between 0.3 and 0.5. It's a quantum degenerated gas, not extremely cold. We have a sample of the order of 10 to the 4 atoms. And as in Brian's experiment, we are going to use the two lowest hydrophile states to encode an effective spin 1/2 degrees of freedom. In the experiment, they also have strong RF that allows to control, to introduce spin flips and to have gradient control. So in this experiment also, we are going to take advantage of the existence of a Feshbach resonance close to 202 taus. And this is going to be our way to control interactions. Let me mention that there has very interesting investigations that were done before close to the untitled point. And the interesting part of this region is that the behavior is universal. We have a lot of Martin talk yesterday where we can have a universal scales close to the unitary point. However, and there has been very also interesting investigation of this region in 2D in Michael's Cole group. But we're going to switch to the less stern regime that is actually the weakly interacting regime. Actually, already in 2008, experiment by John Thomas observed that very close to the 0 point crossing, just small changes of the tuning generated drastic changes of the behavior of the gas. So this is the regime that we want to study a little bit more. So the way that we're going to probe the spin dynamics with a standard Ramsey spectroscopy, basically we start with a spin polarized gas at time equal to 0, that is by definition non-interacting, and then we apply a pi-half pulse, and this pi-half pulse creates a coherence proposition along the XY plane with maximum transverse monetization. Then we wait some time t, and then the system freely evolve, and then what we do is that we measure the total transverse magnetization, that is the length of the connective block vector in the XY plane, and that is defined, can define in terms of the connective spin operator. So SI is a spin operator acting on particle I, so we look at the collective observable that can be measured by applying a second pulse, pi-half pulse, and then measure the population of the up-down spins via Sterninger Black. So some important point is that because we have a balanced gas, equal number of spins up and down, and the magnetization is conserved during the dynamics, then expectation value of LC is always 0, remain constants of the dynamics, and actually we can interpret this transfer magnetization as the total magnetization of the gas. That's what we measure. Alright, so let me start by discussing the single case. That is the case of a non-interacting gas, where we have the atoms in a 3D trap, it's an harmonic trap. We have the particles populating the non-interacting harmonic oscillator levels. And the point is that because the two states have a slightly different magnetic moment, the curvature of the trap that they experience is slightly different. So it's a common frequency plus minus delta, different trapping frequencies. And the point is that these different trapping frequencies translate in a slightly energy difference between the two spin states. So in order to model the spin dynamics, therefore we can imagine that the atoms are frozen in an energy lattice where the lattice is in energy space, so the atoms are in each harmonic oscillator levels that are eigenstate of the system, and then during the dynamics, the magnetization dynamics is determined by the slightly different mismatch in trapping frequencies that generate some spatially some inhomogeneities in this energy lattice that are proportional, that they and the Hamiltonian can be characterized in terms of this HI and SCI. So these are Pauli operators acting on particle I that is in the N harmonic oscillator level. So the point is in the experiment, we can control the HI by, of course, the curvature and determined by the magnetic field, but also we can impose vector line strips that can control the polarization of the beams that form the dipole trap and can introduce corrections to this HI. So if you look at the dynamics during the Ramsey time, the dynamics is going to be extremely simple, because what happens is that each spin is going to process at its own rate that is different from one to the other. And what we will see is dephasing. So if we start with if you look at the total magnetization as a function of time, very quickly, at 100 milliseconds, after 100 millisecond lifetime, you see a demagnetization of the gas, and that is very well captured by this spin model. There are some imperfections in the experiment, some small linear gradients that cause some of these small oscillations, but overall, this spin model, that is the red solid line, captures very well the phasing or the demagnetization of the gas, non-interacting gas as a function of time. Another way to understand the dynamics.
Is this 3D track?
This is a 3D trap. Another way to understand the dynamics that is going to be convenient to look at the interacting case is try to look at the conservation, or look at the total S, that is the eigenstate of the S square operator. So you see that because we start with all the atoms collectively pointing along the same direction, they're occupied with the manifold that is fully symmetric. So the atoms start with S equal to N1/2, because this Hamiltonian doesn't commute with this operator, then as a function of time, the gas is going to demagnetize and populate with others, decay manifolds as a function of time, and this is another way to characterize as dephasing. Okay, and the demagnetization is determined by the variance of this inhomogeneity. Now, let's try to go to the weakly interacting regime. So we are going to really operate at a very small scattering length, where we are going to imagine that again, the single particle harmonic oscillator nodes are a good eigenstate of the system, because the interaction energy is so weak that it's energetically suppressed. It's very, very costly to make the atoms change harmonic oscillator modes. Those cost a lot of energy, and instead, what happens is that you can determine or understand the dynamics as an spin model, where we have the term that determines, that causes the dephasing, the non-interacting term, and the interactions are going to be just exchange interactions that are determined that, this Si dot Sij, these coupling constants Jij are going to be determined by the scattering length and also by the overlap between the different nodes. So it's going to be a spin model in this energy lattice. And actually, this type of modeling is what we have used, for example, in the clock to measure the dynamics when the atoms are interoperated. So notice that, however, in contrast to the clock, there is a magic wave lattice. Here we have this Hi that is going to introduce the magnetization of the gas. So now, because these two terms do not commute, even though at time equal to 0, the system is fully polarized, and therefore non-interacting by definition. As a function of time, the gas can't start to interact, because the spins are going to precess at a different rate, into making them distinguishable. So this is kind of the model that we want to explore. The idea, and this is the most important point, is that this exchange term, let me point out this exchange term is ferromagnetic, because it means that if the interactions are repulsive, because all the spin lines, they are not interacting, and it's going to cost energy to flip a spin. But because it costs an energy, these terms introducing a gap protection that penalizes spin flips and wants to maintain the gas alive. So another way to understand...
What is the tornado fighting?
The dephasing, the spin flips.
Right, I know. I'm just wondering what the weird germ thing is.
Yes, well, the spin flips are bad for us because they demagnetize the gas. So the idea is that these exchange interactions are going to open a gap that is going to protect the system and wants to remain aligned, keep them the state ferromagnetic. So this gap actually is going to compete against this dephasing that is introduced by the single particle term, and the strength of the gap is going to be determined by the average coupling of the coupling constants that in the anharmonic oscillator have. This average scales proportional to the scattering length, inversely proportional to the square root of the particle number. So overall, the gap grows like the square root of L, and therefore, the more particles, more protected the systems against this demagnetization. So that's the basic idea that we want to explore. All right. Even though I'm introducing here kind of a quantum picture of the dynamics, a very simple and intuitive way that we can also interpret the gap protection is by going to a Winfield picture where we can see that each spin is processing around its own magnetic field, and this magnetic field is composed of two terms, a single particle term that is introduced by their own HIs, and the magnetic field generated by the other atoms that is a collective spin, is around the collective magnetization generated by the rest of the particles, the sum over IJSJ. So the fact is that this acts as an time-dependent magnetic field that is generated self-consistently and adjusting as a function of time that want to maintain the atoms alive. So this idea of this Winfield picture of the dynamics is also called identical spin rotation effect and has been used to describe the synchronization into lithium atoms in these experiments with magnetometers. And maybe I'm repeating also something that June explained in his talk yesterday. The idea is that if you have non-interacting particles, then if you think of two spins, each spin is going to be phased because it's going to precess as its own rate that is different. But this term introduces a collective magnetic field along which the atoms want to precess. And because they want to precess along these directions, they try to rephase the sample and try to keep the spin alive. So this self-refacing term, as I said, has been seen in many cases before in other experiments, even with bosonic particles. But the beauty of this Winfield picture is that it's allowing also to connect with a very powerful formalism that in condensed matter people have derived to understand the dynamics of BCS superconductors. So what is the connection? The connection comes from the fact that is now you think about a BCS superconductor, then the dynamics is characterized by either the Cooper pairs that are spin down and up with K and minus K, or empty sites. So if people use the so-called pseudo-spin Anderson mapping, where they identify the Cooper pairs as a spin up and the empty site as a spin down. And when you write Hamiltonian, assuming that terms that have only individual broken pair are energetically costly, so they do not participate in the dynamics, the Hamiltonian is determined by the kinetic energy term of the Cooper pairs that have different energy to the empty sites. And then this is the contact interactions. These are in momentum space, so the interactions are all-to-all and collective. K and Q are the momentum modes. And you can into some of these terms, you have a collective S plus S minus term. So when you can see this Hamiltonian is very similar to the one we have. If we have an additional C squared term, but because the magnetization is conserved and actually zero, that term doesn't matter. So the Hamiltonian is actually the same. This Hamiltonian belongs to a class of what is called Richardson Odin models, sorry for the pronunciation. And actually, these models have been shown to be integrable. And the way that the dynamics is described is in terms of this order parameter that is expectation of S minus, collective S minus, that again is equal to our contrast. And in the case of the superconductors, as I said, is served as an order parameter of gap function. So the point is that there has been a lot of work that have taught us how to exactly solve the Winfield equation in a closed form. They actually admit an analytic solution in terms of what is called the Lax construction that says that there is a conserved quantity that is the Lax vector that can be written in terms of has information of the spectral properties of the dynamics, And by determining this initial value that is set by the initial conditions, we can determine how the system evolves as a function of time analysis. So this lab construction has been used to model the dynamics of quenches in superconductors many years back. So if you see, I know in Troy's scope to call all the papers that was written since 2004 on the dynamics of this glass construction of superconductors, even for Tony Lega, 2005, 2006, and well, many papers, even 2015, trying to improve this construction of the lax parameters of superconductors. And there were not too many experiments actually to test that. In 2015, there was an experiment in Japan that were induced quenches in superconductors that had seen small changes and oscillations of the order parameter at twice the gap frequency. However, these experiments, the experiments are complicated because they need ultra-fast pulses to observe the dynamics, and most of the case, the quenches were extremely small. On the other hand, here we can have the probability to quench very strongly our superconductor or our Fermi gas. All right, so just to make the analogy, so in our case, we have a specific type of disorder or inhomogeneity, and assuming the all-to-all approximation to gain some insight of the gas construction will give us, actually the gas construction does predict two different dynamical phases that are separated by an order parameter that is determined by the collective magnetization, and there is a different behavior and a non-analyticity at a critical point. So in one phase, that is where the system demagnetizes, is phase 1, and the point is that all the roots of the lax vector are real and give rise to demagnetization, but above the critical point, there is a pair of imaginary roots that are non-zero, and they're stabilized and have a non-zero steady state. Actually, you can derive analytic expressions for this collective magnetization that are mainly determined by the variance of the disorder, and for the specific case of one-dimensional systems, that makes an analytic solution that is exact. For higher dimensions, this is more not exact, it's similar, but we have beta and alpha to have some fitting parameters for this form. But in 1D, you can see that this is the solid line is the exact solution of the meaningful equations, and the dots are actually coming from the lax construction. So it's a good description, and moreover, we can associate to the other parameters some oscillation frequency that is one-to-one related to the steady state value of the other parameter that again become non-zero beyond the critical point. So this is the all-to-all behavior. These are now the experimental observations. There are different traces that are taken as you vary the scattering length from weak to strong. So you can see that the system demagnetizes, and at some point you see stable oscillations around a non-zero value. To summarize the dynamics and the character of the phase transition, there are some traces, and the dots are the experimental data. The solid line is mean field theory that is from this spin model that I described before. So you can see an abrupt change when the system demagnetizes, and then oscillations around an equilibrium non-zero point of the magnetization. And here, at 100 milliseconds, we see a jump in the total S, the collective magnetization, that is very well described between the experiment and the theory. And just to look at the significance of the different theories, here is the all-to-all case that is not very well agreeing the all-to-all case with the non-homogeneous coupling constants for the collective magnetization, but for the oscillation frequency that we obtain from the experiment by fitting to a damp or sinusoidal oscillations, you see that the all-to-all theory and the experiment and the inhomogeneous theory agree very well, and you see a very clear signature of this jump and the manifestation of a dynamical phase transition in the system between a phase 1 and phase 2 phase. All right, so we can explore the richer at the broad level the phase diagram, and now we can also tune the inhomogeneity by introducing, by controlling the star chips. So we can change the homogeneity for different values, and this is the value of the contrast as a function of the interaction strength. Well, here you also look at the scattering length, and we see in all the cases that is a region where the system demagnetizes, and after a critical point, you see that the contrast stabilizes to a finite value, making the system align and lock. We can also look at traces perpendicular to the phase diagram, just changing the disorder and keeping the interaction constant. And what you see here, for example, is that in this case, the magnetization remains stable, but at this point, at some point, and especially at this point E, the system is demagnetized. So we are seeing a strong evidence of the phase diagram that we expected from this collective Heisenberg model. And then you might ask about the validity of the theory, because we are assuming a spin model that is not exact. So we wanted to explore a broader range of interactions to see up to what point our model is valid. And you can see that here we are going to explore scattering rates from -100 to 100. The experimental points are kind of symmetric, so you see the protection at a positive and negative values of the scattering length, but you quickly see at the magnetization for strong values of the scattering length that is inconsistent with the gap protection, because of course if the theory, the spin model were right, you will remain alive. So, and this demagnetization is attributed to the existence of spin changing collisions that, and we model this is the red line on the theory by a simple dephasing with a rate that is consisting of a single particle term and also a term that is quadratic in the scattering length that is going to characterize these spin changing collisions. So actually the parameter gamma that we find that fits well the experiment is very consistent with a kinetic theory calculations for the proper density, temperature, and polarization of the gas. And we see that the model fits very well. We interpreted this very simple fit into a good approximation, because in this case there is no coherences, or quantum effects kind of are not very important, and just a simple diffusion model maps the dynamics. So now the question is there any way that we can see better the validity of the spin model? And the answer is, well, what about if we use the capability to control the interactions to undo the dynamics, change the sign of the Hamiltonian to change the sign of the Hamiltonian that determines the spin model, and see if we can completely reverse the dynamics. So the point is that yes, in principle we can have, if you look at the spin model, we can change the HI by applying a pi of pulse in the middle, and we can change the sign of the scattering length from positive to negative. So basically this perfectly undo the Hamiltonian of the spin model, but we are not undoing or changing the sign of the mass, for example. So the full Hamiltonian is not changing completely, but the spin model is completely changing, so we can test the validity of the spin model if the dynamics is reversed in some way. And actually, this is exactly what we see when we apply the time reversal. If we focus on the region where the spin model is expected to be valid, between -20 and 20, you see that these are more data expanding this region. We see that actually the dynamics is fully reversed in this region instead of this fast CK here. So we validate the spin model, and actually because the model that describes the full dynamics is proportional to this gamma parameter that is the same in the two cases. So we validate the spin model, and that the simulation of the Heisenberg model with a weakly interacting gas. Okay, so that's great. So how much time I have to say?
6 minutes.
Okay, perfect. So now the last part that we are asking ourselves is that what actually is the role of quantum fluctuations. So far I'm discussing that the spin model, the spin model and the mean field treatment of the spin model was producing a good formulation of the dynamics. But the point is that if we look now at the different interactions, so if we look at the mean field dynamics for different values of the interactions, we see for weakly interactions at the mean field level in the case, and as we go to stronger interactions, and we see the oscillatory behavior and the full stabilization for strong interactions. But the question is how long this behavior is valid, even just for a simple formulation of the spin model. And what we find when we are able to include quantum fluctuations, that and as when we can explore the dynamics for longer times, not only up to 100 or 200 milliseconds, but we can go to longer times. Actually, we can see that even though the mean field picture is very good at chunking the model, and we are attributing that to the emergence of quantum correlations that are lacking at the mean field level. So the question is if we can see the emergence of these beyond mean field terms in the dynamics. Well, it might be that in Joseph's experiment it's going to be a little bit hard because we need to go to much longer times, but hopefully the clock that it can go to 10 seconds, we should be able to actually see the emergence of these beyond mean field corrections, and actually this is consistent with the formation of spin squeezing that is happening in the system. That could be a useful meteorological resource. So, okay, so with that, just let me summarize, and I said that we have, we discussed a weakly interacting gas of Fermions, and we showed that we can simulate the Heisenberg model with different interactions. So we mapped it to a special case of Richardson-Hall model. We were able to show the different phases by control over the interactions and the Feshbach resonance, and control over the homogeneity using vector light shifts. We saw a signature of the dynamical phase transition, approach changing the behavior of the gas from stable to demagnetized. We attributed this with the existence of a gap in the dynamics that stabilized a ferromagnetic state that, of course, is not the stable, it's not the ground state at all in an equilibrium phase matter. We see the degree for a large number of particles and both in the magnetization and the oscillation frequency. And we were able to validate the spin model by doing time reversals. We did a many protocol, and also we see the time reversal in the regime where the spin model is valid, but the breakdown of the spin model at strong interactions. More details you can find in this paper, in the archive paper. And let me just finalize my talk by advertising that we have a new research and as assistant professor at CU that on quantum information science is an experimental research. So if you're interested, please apply. And also we have open postdoctoral positions. And with that, thank you very much.
So you mentioned that it might be difficult to see the quantum fluctuations because of time scales. Is it because of decoherence?
Because particle loss, yes. So yeah, when you look at the experimental cases, you see that after 100 milliseconds, here at the long-time dynamics, here you can see a slow decay. And this is slow decay. I mean, this is only 100 milliseconds. If you go to 500, we know that there is losses. Even, I mean, there is losses, and also the fact that there are no clock transition, additional time-dependent fluctuations of the magnetic field.
So the TWA was for the closed system?
Yes, the TWA. So the TWA was mainly for our theoretical simulations, assuming the same parameters of the experiment, but ideal conditions, and the experiment most likely was good up to 100 milliseconds, but at long times we could not match. But June's experiment has 10 seconds coherence time, so most likely we would be able to see beyond mean-field effects.
About speaker, like what if the time reversal actually is not symmetric, and then after this time reversal data becomes symmetric all that to the data, so what will happen over there?
So because the continuing not
The
symmetric.
spin model, like the one we showed at the
Okay, when we don't do the time reversal, this case.
yes.
So yes, so what happens is that the system demagnetizes as there is weak interaction. At the strong, when you increase interaction, you see that the magnetization is preserved. But for strong interactions, the system demagnetizes again. And the demagnetization is because the spin model breaks down here. So the spin model assumes kind of single particle harmonic oscillator levels that are populated, but when you start to have very strong interactions, particles can jump, have collisions that change the spin.
But clearly when you apply the dipoles, like the data, like becomes
when they apply the pulse, so what happens here is that, yes, so when you apply the pulse, these become flat. So I mean, these are just small points. So this is a blow up of this region, and there should be no dynamics.
But I'm talking about like at a higher, like a 400 or something.
Oh,
You see, like right now it's like similar.
yes, there might be some systematic effects that can be that are, I mean, there's some. Yes, exactly. There are some systematic effects that can happen that are different between these two. But overall, yes, so you can see here the two are not agreeing very well, but here it agrees very well. Yeah. But this is very phenomenological in this part. So we just model it by a decay exponential proportional to the square of the scattering length. So in our case, it's fully symmetric because the mode changing coalition should be proportional to A squared. So, but yes, so that's a good point. What is the asymmetry here? The slight asymmetry here.
I have two very quick questions. So in the future you go down analysis. The analysis that is done, the system is actually, the photonic itself is Parthenon, an approximation is Parthenon conservative. So how important that is in dynamics? I mean, because
yes, so you are saying the terms that are not, that break pairs, the pair breaking terms.
right.
These are similar to our mode changing coalitions, kind of.
Right.
So,
So how does it affect the interpretation since there's no, and the second thing is the effects of unharmonic.
yes, exactly.
I'm worrying about that because it's, if you really quench those things up very much, higher states, I mean, it should be a big effect.
Okay, so let me answer the two questions. So you can see that the effect of more pair breaking terms are going to be relevant when you have stronger interactions. And that's what we see here. So there is this e to the minus gamma 8 here, so there is this decay term. That this is a single particle term that is independent of the interaction because some linear gradients.
But it's phenomenological, right? You're adding by hand. Right?
We are adding it by hand because it's very hard to model dynamics, but the dynamics is very well reproduced by this very simple diffusion model. As I said, because as you go to stronger interactions, there is not too much coherences that you have to keep track. So the terms are going to be there, but what we emphasize is that they play a role for stronger interactions. And most likely it's also the dynamics of superconductors, where these pair breaking terms are going to take place, but they are going to be dominant at longer times. At shorter time, maybe the dynamics is really dominated by these non-pair breaking terms. Now, inhomogeneities are actually good for us, because actually if you have, in fact, inharmonicities are good for us, because the fact that the trap is completely harmonic can introduce some undesired resonance, because you can see that you can go to n plus 1 and n minus 1 doesn't cause energy change. So we are comforting homogeneities in the trapping potential. They help because they actually did favor mode changes, because now it's enharmonic. So you have to one particle in n mode n, the other in mode m, then n plus 1 and n minus 1 are not resonant. So actually they favor the stabilization of the spin model. And what they do is that, for example, here, our the JIJ that we compute from their overlap harmonic oscillator models, we have to correct it by 80%. So we have to, if you look at the theoretical calculation of the JIJ or the mean J bar, we have to multiply by 0.8. And when we do an analysis based on these anharmonicities, actually it's consistent with the anharmonicities that we expect from the experiment.
Okay, so the comparison to the experiment in theory is corrected by that factor?
It's corrected by a factor of 80%. Mm-hmm. Yes.
So a question on semantics. So what should we really call now dynamical phase transition? As you showed nicely, ultimately everything is decaying. So what would be your definition of calling something dynamical phase transition?
Yeah, so, okay, that's an excellent question, and actually there are different definitions, because not only there is the chart, so there is a different definition of a phase transition that we were using in another type of papers, that it was singularities in the Lord with echo. That's another definition of dynamical phase transition, and if we are strictly speaking, dynamical phase transition should apply for trivial dissipative systems, where really a steady state is independent of the initial conditions. So what we call dynamical phase transition are following just to reproduce the different dynamical phases that you happen to see at the mean field level. So at the mean field level, if you solve the mean field tutorial, you see that it doesn't decay. Ultimately, it decays when you account for one, experimental imperfections are beyond mean field corrections, and perhaps this is why it's so. Yes. So the idea of the mean field theory oscillating
So in
forever.
this sense, you could say there's an underlying effective mean field Hamiltonian that has a true dynamical phase
Exactly.
transition that's smeared out by
Exactly.
the defacing.
Exactly.
I
And so,
like this language. Yeah.
okay.
But in an isolated or interval system, it can only be put thermal phenomenon, right? Because as you pointed out, and as Maria pointed out, if you thermalize eventually, it will be an equilibrium phase transition. So if you achieve separation of timescales where photon annihilation happens, and later on you decay, then in that transient you can define it this way.
Modulo MBL.
Modulo MBL and modulo what Maria said, that the system is never dissipated, so the non-equilibrium state is stable, and then you can go in this way.
Other questions?
Can you go back to the PWA plot that you showed? So I was just wondering if there was a clear separation time scales between the decay and the sort of oscillating behavior that showed up in the theory?
Yes, there is.
There's an oscillation somewhere.
Oh, no, okay.
Yeah, so I mean, it looks like the time scales are comparable for the decay and the oscillation. You know, there's some separation, but obviously not a huge window here.
Well, depends on the, so the oscillation become faster as you go to larger values of the interaction. So yes, I mean, I think it depends on at the transition region, it's going to be tricky to define.
So if I were to fix the value of the interaction and use all-to-all couplings instead of the inhomogeneous couplings, does that also make the plateau bigger?
Well, actually, if you strictly look at the oscillations of the order parameter, even at the mean field level, doesn't survive up to the steady state. So you see here, the oscillations are even slowly decaying as a 1/square root of t. I don't know if this is your question. The oscillations, there is a frequency of the oscillations, but the frequency of oscillation is down. And in the steady state, you don't have oscillations. The order parameter is S e to the I omega t. So the amplitude of the oscillation is 0 at very long times. So
what about the decay of the mean? How does that depend on,
this decay of the mean
Yeah.
is just, you can, actually the dynamics maps exactly to an IC mode. So you can do the dynamics, and this decay rate is e to the minus n, so it's proportional to e to the minus n chi squared t. So the decay rate is 1/square root of n, and this is very consistent with the term.
Coffee also is the perfect time for discussion.